More analysis of polynomials. Cool. We are going to be introduced. You've already been introduced to this in past math classes in Algebra 2. So here it is again. The fundamental theorem of algebra. Just got to kind of go with it. I can't really show you exactly why this has to be true. Smart mathematicians proved it. But all the fundamental theorem of algebra says is that your degree of your polynomial has to equal the amount of roots. Now, roots being zeros, understanding that roots have multiplicities, that is also part of your analysis. If you have a function, what's great about the fundamental theorem of algebra is you look at it and you know you're going to have 3 roots. Your goal is to find them. Ready, set, go. Factor out a greatest common factor is always a good first step. You're going to try to factor out negative 4x, and it's not going to work. So then you will factor out a negative 2x, and you will realize that you have a quadratic where a is not equal to 1. You guys go back to the unit 0 test when we reviewed how to factor quadratics with a is not 1 and factor this. 2x squared minus 5x minus 12. Go. Factor it. Take some time and factor this. Tell your neighbors, like, what is the key thing? Like, do it. Come on. We got this. Like, the last class that did this really struggled. We had a lot of kids just sitting there, clicking their pens, being like, oh, I'm not going to do this. But not this class. This class is different. This class is going to show me that they remember how to factor polynomials and a is not 1. We got people factoring by grouping. Great. We got people using the box. Great. We got people going for it. Great. Just got to figure it out if you go for it. That's not going to work out. Negative 8 times 3 is not negative 12. Okay. 2x times 2x. Yeah. It's not right. Wait. How? This is not the correct factored form. These are the correct solutions. They're cool. That's all.
Wait, can you show the box?
Sure. You want to see the box again? Linda, here's the box. I love the box. You got the two numbers? Negative 8 and 3. Ready for the box? We you split up negative 5x into negative 8x and 3x, like that. Cool?
Oh, wait.
You don't like the box? Listen, I don't care which way you do it. Just get it right. Now, what you should get is, and what I love about the box is, like, there's got to be something here, 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 and here. You got to have 2 things times 2 things. The next one we're about to do, a lot of people, when they factor by grouping, might make a mistake because of the fact that they'll forget something. X times 3. 3 times -4. It kind of just works out if you know multiplication, you know distribution. This is like a quick and easy way to factor. We expected 3 roots. We get 3 roots. X equals 0. Multiplicity is 1. X equals -3 halves. Multiplicity is 1. X equals 4. Multiplicity is 1. 3 roots. Hooray. Okay. Now do the next one. If the first one didn't go so well, go. Now, how many roots are we expecting, Ford? 4. We're expecting 4. Okay, that's good. That's how the fundamental theorem of algebra kind of helps us. Now you find them. Go. Come on. No. These are right. You're good. Oh, you're looking at these 2 already?
Oh, because there's multiple.
Yes. Roots include multiplicity, my friend. Roots includes multiplicity. Having a root twice, that counts for 2 roots. You expect 4. You might not get 4 different ones. Yep, you got to factor that. Holy cow, guys. Oh, first things first, Mike. Factoring is undoing distribution. After factoring, you better get something that's distributed to get this. Okay, 9x squared, 6x. Don't stop there, that's wrong. Why plus 1 and not plus 0? Because -3x squared times 0 is not -3x squared. Think about the distribution of the 3x squared. We got to get -3x squared. First things first, make sure we have a plus 1. Nice. No, look, you need this plus 1, Nancy. We were just talking about that.
Oh, okay, I see that.
What do you mean don't see that? You should have had that.
Oh, I did. You see right there. And I erased that.
No.
I'm lost them.
Now, cold cricket, let's pretend I didn't know how to factor 9x squared plus 6x plus 1. Right? That would stink. But would there be, if you didn't know how to factor 9x squared plus 6x plus 1, could there be some sort of backup out there that I could use to help me? Tell your neighbors, what is the backup method if you can't figure out how to factor? Thank you, we could use the quadratic formula. So let's say you didn't know that this was 3x plus 1 squared. 3x plus 1 times 3x plus 1. You could have just been like, I give up, opposite of b over 2 times a. That's going to be gross, but whatever. B squared minus 4 times A times C over 2A. So you realize, oh, negative 1/3. Negative 1/3 plus 0, negative 1/3 minus 0. That's showing me that I have 2 negative 1/3. But you guys, however you want to factor to get 3x plus 1 times 3x plus 1, please do it. If you'd like to write it as 3x plus 1 squared, great. What you are seeing is your 4 roots. Mr. Messer, I only see 2 roots. No, I see 4 roots. I have this one that has a multiplicity of 2. I have this one that has a multiplicity of 2. That's 4 roots. Got it? Cool. All right, let's try another one. Right here, H, go. I'm expecting 4 roots. Let's find those 4 roots. Go. And listen, I'm going to come around and tell you you made a mistake. Don't be offended. Don't be dejected. Everybody makes that mistake. Sorry, you just made the mistakes that everybody makes. Sorry, Swanee, you made the mistake everybody makes. Sorry, you made the mistake that everybody makes. Good start. I don't know what to do there. Who else is going to make the mistake that everybody makes? You did, but then you erased it. You made the mistake, Alan. Don't move past this one. That one's wrong. Sorry, that's wrong, but good try. I love the doodles. I don't like the answers that you are not providing. I don't like that answer. You made the same mistake. Boss, I love what you're doing. You know? Oh, Kutcher, look at you. What's the square root of 4?
Oh, well, I was
Yes, you were. Nice. Bang. Sorry, Nancy, you made the mistake that everybody makes. Sorry, Linda, you made the mistake that everybody makes. You got the right track. You're good, Ronnie.
I'm good.
Yeah, you're good. Hey, look at us. Did you fix it? Yes. So the mistake that everybody makes. The mistake that everybody makes. No, you didn't get it.
Did I?
You didn't get it. You're close, sir. Is, and this is super important, guys. You are stuck in real land. You think everything factors. You think x plus 2 times x plus 2 is x squared plus 4, but you know better than that because this is x squared plus 4x plus 4. And then you're like, oh, no, my bad. It's x plus 2, x minus 2. And then you realize, oh, nope, that's wrong because that's x squared minus 4. And then you try to do some crazy things with a negative in front of an x, and then you'll just have negative x squared plus 4, and that doesn't work. So what you don't realize is not everything can factor into real solutions. We actually have solved this equation before, and when we've solved it, we've gotten an imaginary solution, which actually means this factors, but to x plus 2i, x minus 2i. You don't have to do that. What you do have to do is find that 2 of your roots were complex. We have complex or imaginary solutions. And then 2 of your roots were real. We are now going to see that sometimes polynomials will not have all real roots. You could have some complex or imaginary roots. Okay. You're going to have 3. Find them. What's your backup? Kutchler. Brun's got it. What's the other one? You need 3. Yep. Nope. Don't say that. X equals 0 is 1. Great. Now I need to find the zeros of that quadratic. What's your backup if you can't factor? Because that's what we do. Okay. Here's one. Here's the other one. X equals the opposite of b over 2a plus or minus. Don't be annoyed by the quadratic formula. It's not that bad if you do the work just to the side. B squared is 36. 36 minus 4 times 1 times 10 is 36 minus 40. That's not that bad. If you don't want to use the quadratic formula, go ahead and complete the square. Yeah, I don't want to do that either. It's actually not that bad. The square root of -4 is the square root of 4 times the square root of -1. The square root of 4 is 2. Don't forget to take the square root of numbers. Okay? And the square root of -1 is I. Giving me 3 plus I and 3 minus I. Which actually means, hold on, that we could factor this to be x times x minus 3 plus I times x minus 3 minus I. But we don't have to do that because we were just asked to find what are the roots, but just keep this in mind for the future. Let's do one more for fun. Okay. The next one, there are my 3 roots. This one, go ahead. Do this one, please. Okay. And then we're going to talk. The F on the left. Wood, you have lost your phone privileges for entire class periods from now until the foreseeable future. So, while everybody's done with their quiz, fiddling around on their phone, you could sit there in silence and do homework or something. Yeah. Who else is trying to sneak in their phone right now? Horribly. Don't care.
I have a question on this. Why not? Like, I know why. I know that we never got it. On the homework from yesterday, on the quiz from yesterday, we had I.
No, Woods, you're missing it. What's x plus 3 times x minus 3? Distribute that. Yes. X squared minus 9 is x plus 3 times x minus 3. We have x squared plus 9. Woods, were you here when I was talking about how you might think of doing this, but you were wrong? Why? Because you were probably on your phone. Because then it would be x squared plus 6x plus 9. That's not right. So, turns out the factored form of this is actually x plus 3i, x minus 3i. You don't have to know that. Really, it is something we need to kind of think about for the future, but You set this equation equal to 0, Woods. You get x squared equals -9. You get x equals plus or minus 3i. Got it?
Yeah, I got it. So I have it.
So, x equals 0 has a multiplicity of 2. Those are 2 of my roots. Here are my other 2 roots. Now, please tell your neighbors, what do you notice about all of these polynomials that have these complex roots? What do you notice about all the complex roots? Talk to your neighbors. Yes, complex means they have eyes. Good. That is like definition of being complex. You're going to have to be imaginary. You have the eye. What else do you notice? 0 is already kind of is something common with the 3. It doesn't have to be.
Plus or minus is always true.
There's a plus or minus for all of them, okay? It looks like there's always going to be pairs of them. But then I have a question for you. Gosh, I'm moving around a lot today. You guys are really not locked in. Could I just have one? Could I have just one imaginary root? Could I have just one complex root? Could I have an x cubed equation that has one real, another real, and then one imaginary? Is this possible? That's the question. Well, here's an example that might show you if the answer is yes or no. Here is a very simple equation. We have a polynomial with a 0 at 0. Its multiplicity is 2. And then a 0 of I, multiplicity 1, which means we just have 1. Let's write that out. Okay, y equals x equals 0 multiplicity 2. What would be the factor? Cool. And then x equals I multiplicity of 1. What would you write that out? X minus I. Is this a polynomial? No, it is not, because when you distribute it, what do you get? X cubed minus ix squared. Guess what? You can't plug this into your calculator and get a graph of a polynomial. Day 1, we talked about what's a polynomial. You have to have numbers. They have to be real numbers as coefficients. You can't have a coefficient of I. This is not a polynomial. Now, I'd like you to try something for me. I'd like you to multiply the pair x plus I and x minus I together. Please multiply, distribute x plus I times x minus I. And tell me what you get. Linder, I'm going to wake you up real fast. Go ahead, do the distribution. What do you get? Close.
No, x squared.
You are not distributing everything. No.
X squared minus 1.
No, it's
Nope.
what is I squared?
Yes. Ready? X times x is x squared. X times negative I is negative ix. I times x is positive ix. I times negative I is negative I squared. We get x squared minus I squared. Cool, we good? What is I? The square root of negative 1. What is I squared? I squared is the square root of negative 1 squared. The square and the square root will go away. I squared is negative 1. That means this is x squared minus negative 1. That's x squared plus 1. Hooray, yo, when you have a pair, what we call is a conjugate pair, a plus a root and a minus a root, the whole plus or minus. When you have a pair, you put those in like the factors, like x plus the complex root, x minus the complex root. You multiply those pairs together, the i's will go away. What does this mean to you is that you will always have pairs, Linder, of complex zeros. Complex zeros always come in pairs. You always have 2 of them, or 4 of them, or 6 of them. Sorry! Trubik, I'm really sorry. I was really throwing that wood, and I'm sorry that I hit you. I'm really sorry. Are you okay? Did I hit you with the hardest? There you go. Stop messing around.
I didn't do anything.
Stop messing around. All right. Cool. Now, give him his water bottle back. What are you doing? Don't do it.
Go ahead.
Now, if you know of certain factors of a polynomial, the question is, what would the minimum degree of the polynomial be? Well, I know x equals -3 has to be a root. I know x equals 1 has to be a root. I know positive 2i has to be a root. So negative 2i has to be a root as well. This has to be an x to the 4th. If I have x minus 2 plus I, I'm going to have the pair that goes with it. If I have x minus I, I'm going to have the x plus I that goes with it. Oh, I have x equals 0 3 times. I have 3, 4, 5, 6. This has to be an x to the 7th. Okay, here's another one. Ready? If you have x minus 2i as a factor, you have x plus 3, and you have x plus 2i, what must be your degree? Tell your neighbors. I heard 5, I heard 4, I heard 3. Yeah, so this is a trick. You see this on your homework. I'm giving you the pair. I got x minus 2i, x plus 2i. You multiply those two together, it'll just be x squared plus numbers. This is x plus 3, -3. So this little trick at you, just the x cubed. Thanks, Woods. Appreciate it. Yes. Yep, complex zeros. Here, hold on. Let me just make sure everybody's got that. Complex zeros always come in pairs. Cool? All right. Did you see that? Okay, great. Yes, thanks. Yeah, so that's like what is the...
I know it's a 2. What would I write for at least?
Well, it's got to be 3. Like, you're going to have something else besides x minus I. You're going to have x plus I with it. So that's going to be a 1, 2, 3. Your least possible degree is 3. Because complex zeros come in pairs. If I give you, hey, this polynomial has this one complex zero, you know it has to have the other one. Okay? So that's why I'm going to say x cubed. X cubed, yes, the least possible degree is 3. Okay, moving on. What do these complex zeros look like? Well, you can think about how like y equals x squared plus 9 really just doesn't cross the x-axis. So what happens with polynomials with complex zeros is you notice that it's not as smooth as a typical polynomial would be, which is just nice, smooth ups and downs. There's some other stuff going on. This is one little visual indication that there's some complex zeros going on. Now, you are going to be told some information for the next question, whether or not I'm giving you the degree or I'm giving you the amount of complex roots. Use the information, use the graph to then answer the question. You were told you have 2 complex roots. What is the minimum degree of this polynomial? Tell your neighbors. What do we say? Oh, I'm hearing 4 and 6. You guys tell your neighbors. 7? Not a trick question. The answer is it's got to be a 6th degree. You have 1, 2, 3, 4, 5, 6. So you have 6 roots. Your degree has to be at minimum 6. Cool? Okay, next one. This polynomial has 4 roots. What is the minimum degree of this polynomial? 1, 2, 3, 4, 5, 6, 7, 8. The next 2 questions tell you what the polynomial's degree is. This is an x to the 5th degree. This is an x to the 5th degree. But the question is, how many complex roots does it have? Tell your neighbors. Go. What do you think? So, it's a 5th degree, which means we have to have 5 roots. What are the roots you can see? And their multiplicities. So you have 1, 2, 3 real roots you can see. This is an x to the 5th polynomial. It's got to have 5 roots. How many complex roots do you think that first one has? Nailed it. You can see 3 real roots. You can see their multiplicities are 1 because we are not slowing down as we pass through. That means you have to have 2 complex roots to give you your x to the 5th. You can see a double root here, a double root here, and a single root here. Oh, that's all 5 of the roots. If this is an x to the 5th polynomial, therefore there is 0 complex roots. Cool? 2, a fun part of this lesson. This is completely different. It's just like I was doing these problems on the homework video, and I just had to laugh a little bit. I giggled a little bit because I think they're silly. All right. This is a quadratic polynomial, the quadratic equation. What can you analyze to confirm it's a quadratic equation? Tell your neighbors. No. Don't say it goes up then goes down. The rates of change were linear, or the rates of change of the rates of change were constant. Now, we had talked about rates of change when we did the y's divided by our x's. We're not going to worry about the x's. We're going to just make sure they're equally spaced. They're equally spaced. We're going to just worry about the y. 11 to 6 is minus 5. We call this a difference. 6 minus 11. 6 to 3, or 3 minus 6, is minus 3. 3 to 2, or 2 minus 3, is minus 1. These are our first differences. These are the rates of change, because it's like change of y over change in x. Cool. Now, we could have said the rates of change form a linear pattern. Or we can say that the second differences were constant. Quadratics have constant second differences. Guess what? Cubics have constant third differences. Fourth degree polynomials have constant fourth differences. Now, really quickly, I have a challenge for you. If this was 4, what would be the y value? Go. Second difference is the change of the change. This is the first difference. This is the second difference. This is how this is changing. Negative 5 to 3 plus 2, negative 3 to 0 plus 2. What's this value right here? The 11? I don't know. I haven't done it yet. Well, I know that if it's a quadratic, the next step, second difference has to be plus 2. Well, like 1 plus 2 is 3. 3 plus 2 is 5. 6 plus 5's got to be 11. Cool? Ah, shoot. All right, flip. Okay. What degree polynomial is this? And tell me, what is the next value? So what we're going to do is just continue to find differences of differences until the last set of differences are constant. This demands like concentration and no mistakes. You make one little mistake and things go crazy. 3 to 6, or 6 minus 3 is a plus 3. 6 to 3 is a minus 3. 3 to 0 is a minus 3. 0 to 3 is a plus 3. This is why I'm like, I find these are funny. Because it's like a bunch of 3's, and then you go to the next one and you're like, plus 15. And then 51 minus 18 is a 13, 33. Okay. Cool. I don't know what the next one has to be. Yeah, it doesn't look like anything. Now, Linder, find the differences of those differences. You just found the first differences. Let's find the next differences. It's all going to work out, trust me. Positive 3 to negative 3. What's that? Minus 6. Negative 3 to negative 3. Plus 0? God bless you. You're on fire. You're on fire. It's okay. Negative 3 to positive 3. Plus 6. Positive 3 to positive 15. Plus 12. Positive 15 to positive 33. Plus 18. Oh, we're seeing something. Add 6, add 6, add 6, add 6. Oh, the third differences are consistent. This is an x cubed. But tell me what's this value right there? Is it really 108? You guys are already done? All right, great.
In the practice, yeah, the 1/108.
Exactly. Look at that. It came from the same exact function, actually. Yeah, we made a mistake somewhere. Nope. Do you know the formula, Lori?
I learned it like in
So what'd you do?
I can't remember. We did like something like this in this trig, and I can't remember what it was.
I have to think about it. All right. So, you know this has to be plus 6. This has to be plus 24. This has to be plus 57. And this has to be 108. Okay. Let's finish strong. Yo, go.
There's something that works. I can't remember what it is.
I'm sure it has something to do with sequences, but I don't know what it is.
Yeah, I can't remember.
All right, go. You guys are giggling too much. Giggle less. Okay, thanks. Sorry. Sorry. There you go. What's the next point? Yep. One of my students. No. I'll write you a rec letter though. That's what the deal was. No. No. I like gains, but not that much. I try to eat healthy. That's a good idea. You don't want that. It's a lot of money. 0? 29? No, a lot more than that. You guys are giving up too early. No, not.
Is it 125? Bro.
Why are you stopping here? You have to keep going. No, keep going. Keep going. Are your first differences constant? No. Keep going. Negative 43 to negative 5 is positive 38. Positive 5, negative 5 to negative 3 plus 2. Negative 3 to negative 13 minus 10. Negative 3 to negative 11 plus 2. Negative 11 to 27 is plus 39. Is that right? 38.
Yeah, we did do it wrong. What's plus 2? You got one wrong.
This value is not 2. It's like 100 and something, okay? 125, Ratty. Okay, 38 to 2, minus 26. 2 to minus 10, minus 12. Minus 10 to plus 2, plus 12. Plus 2 to plus 38. 36. See? You make one mistake and it's done. And this is 36 too. All right, now we got plus 24, plus 24, plus 24. Okay, here we go. 36 plus 24 plus 60. 38 plus 60 plus 98. 98 plus 27 is 125. That's what that is. Isn't that fun? Oh, I can't wait for you to do those problems on your homework. Hey, on your quiz, I think we go to a 6th degree too, so that's fun. I'm just joking. Yes, I know. You make one little mistake.